Hello folks, in this tutorial number 7 in the current playlist which deals with buckling problems, I'm doing a follow-up to tutorial 4, 5, and 6 where a column has been analyzed using the linear buckling features in the 3D Experiences Abacus Simulia program. In this tutorial, I will be repeating the same problem except that I will perform nonlinear buckling, okay? And the way it's done is that there's going to be two static steps. In one of them, I'm going to be performing a lateral deflection and to introduce some kind of a imperfection effect, and then axially in the second step, compressing it. Now, the problem that we did was right here, and for simplicity, I'm assuming that this is a column with a circular cross-section, and incidentally, because we don't have two-dimensional elements in 3D Experience, the element that is used in 3D Experience is actually B31, namely three-noded linear elements of abacus. And in order to make sure that it actually is reduced to a two-dimensional problem, I have to introduce some constraints so that this beam does not move out of plane and does not rotate in the directions that we don't want to. So the way it's conducted here, we have two static steps. In the first static step, I will apply this lateral load of 100 Newton. That's a very tiny load, realizing that this is 1 meter long and the cross section is 60 millimeters in radius. So all it does, it creates the effect of equivalent effect to imperfection, so that we can actually do nonlinear analysis. And then in the second step, I perform uh, a compression, and this is the oil. This is the number that comes from the Euler buckling formula. Okay, so this is the load that I will apply, and now the reason I did these 3 or 4 back-to-back tutorials is because very often there's more than one load that is appearing in your problem, and I wanted to dig into the situation where there is more than one axial load. There is here a transverse load that needs to be modeled. So those are done in tutorial 4, 5, and 6. So here is the details. The bar is made out of steel, 60 millimeter in radius. The length is 1,000 millimeter, and using a buckling, one end is clamped, the other end is free. And the Euler buckling formula will give you a roughly 5 million Newton as the buckling load. Now, this is the comment that I made in order to basically simplify my job and look at a two-dimensional problem. I impose these restraints here. In other words, obviously the bottom is clamped, but this beam, the entire beam, I'm assuming it doesn't move in that direction, which is X, and does not rotate in directions Y and Z. That effectively reduces B31 into B21 element. Now, because we are doing two static steps, if I use the feature manager by right-clicking on the 3D Experience interface, you get this table, and it shows you that actually the lateral force is in static step 1. You can see that, and in static step 2, axial force is present. Notice that this axial force is not present in step 1. And the lateral force is also propagated in step 2. That's the way things work in 3D Experience / Abacus. Now, let me show you the results, how I'm going to, of course, I'm going to do this problem completely, but I'm going to show you the results. First of all, if you apply a lateral load of 100 Newton with this information on the two static steps, what you get a force deflection curve like that, and you can see that something happens there. And that point is roughly 4.6 10 to the 6 Newton. So it looks like the, 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 the nonlinear buckling, you can think about it as appearing here. Instead of appearing at 5.023 e to the 6, it appears at a lower value. That's because of the obviously the lateral force. Now, if I change this maximum time increment for the second step, the first step is not really that critical. If I change that, you get the same curve. You can see that it's a little bit different. I mean, it's a smoother. Now, if I make the lateral load 1 Newton, and if I plotted this thing, I can't see much in the force deflection curve, but if I zoom in, you see that something closer to 5 will show up. And that doesn't surprise you because 1 Newton lateral load means that, yeah, your load is almost non-eccentric, okay? And therefore closer to the theoretical value, which is 5.023 e to the 6, which is for the fully idealized situation. Now, if I apply a load of 10,000, lateral load of 10,000 Newton, notice that, well, the load obviously is going to be lower. It should be lower. Buckling load can be, thought about something in these areas, 4.4 lower. And even if you make it even further, but look at the deflection. That's a lot of load. That's about a ton of weight, kind of uh, bending that column. Okay, 150 millimeters. That's a lot. If you make it 1 million, look at. I mean, obviously the curve is going to be a much lower value. You can see that, but look at the value, 700 millimeter deflection. I mean, these are all nonsense. Okay, so let's go ahead and do this problem. All right, we go to the experience and make the part. It's very simple. I've done it 4 times already, but we'll do it again in case you are fresh starting from this tutorial. So I'm going to make a line, and the line is a point and direction. Point down here 0, 0, 0, so I'm going to make it 0, 0, 0, and the direction is direction Z, and the height is 1,000 millimeters, 1 meter long. Good. Now, ordinarily, if the cross section is not circular, you need an orientation point here. And I did that in tutorial 4 and 5, but in 6, I said we really don't need that, so I'm not going to bother even making that extra point here. Let me apply the properties here, material properties. So we go to Tools, and let's see now, Tools, yeah, find the material right here, create a material. I'll call it a nonlinear column. Nonlinear column, and it's December 27, 2023. Okay, we say okay, and we're going to input the data in just a minute once this thing actually is created over there. Right here, nonlinear column, December, so we're going to say apply, and I'm going to close this and apply to that part. Check the green check mark, and I go and input the values. Okay, so it's a structural, abacus multiphysics, mechanical, elasticity, elastic, 200,000 megapascal. That's properties of steel. 200,000 megapascal, and Poisson ratio 0.3, although I don't need this, but I'll just put it in. Okay, so now we're going to go and mesh this thing. So we go to a different application, which is structural model creation. That's basically for meshing purposes. MTFEM. Okay, and click on the mesh tab, and here's the beam mesh. Select this, and you make 10 100 millimeter long beam elements. You say okay. It's meshed. You see that? And then we go to properties. First of all, the profile of the cross section on the beam section, beam profile. This is going to be circular, And that's just the name profile, beam profile one. If you can call it my profile, etc. And the radius is 60 millimeters. Okay, now that we have created the profile, we can create the beam section. So beam section, select the line and select the profile, what's called beam profile. And I don't need an orientation point because this is a circle. Otherwise, I would have to go and create, I mean, basically select a point to be able to do the problem. But this is a circle, it doesn't matter. Good. Uh, Now, this is pretty much done. Let me quickly save this. Keep in mind that I can do the steps one at a time. I do step one, run it, and then I do step two and then run it, or I can create both of them at the same case and then run them simultaneously. But I'm going to do it one at a time. So let's switch to the simple structural scenario creation. There's also mechanical scenario creation, which is a more advanced or has more advanced features in the finite element capabilities, such as explicit, but we don't need it. So we select it's a structural problem. We select the mesh that we created out of this pull down menu. We select the mesh that we created. All right. Okay, so here it says no procedure exists. Of course, that's why there's a red exclamation mark. You click on the procedure and you select the static step. That's going to be static step one. And these are the default values. I'm not sure what I put in here. Let me use the same values, although that's really not important. 1 point minus 6. Okay, let me go ahead and change that. It really doesn't matter. But this number, I'm going to make it 0.1. And this one, to be consistent with those slides, I'm going to make it -6. That's really, and let me see what else they have here. And the maximum step size, this is the one that we are doing. This is the step that 0.01 and 0.1. Okay, so let's go make this thing 0.01 and 0.1. And I already made that thing to -6. And make sure that, I mean, obviously it is, the nonlinear geometric effect is checked. This is by default checked. So we want to say yes. Okay, so let's apply our boundary condition. The boundary conditions, the bottom is clamped. So what I'm going to do, instead of using clamp, I'm going to use fixed displacement. It's the same thing. So that bottom point is clamped. All degrees of freedom are fixed. It's just that I don't like the icon for clamp. It's just a yellow ball, which doesn't make sense. And then fixed displacement on that entire edge. This is to avoid moving in the X direction, so that essentially becomes a beam, two-dimensional beam problem, and rotation Y and Z are fixed. Okay, that turns it into a one-dimensional problem. And now we're going to apply a load. The load is a force. At that point in the direction Y, we decided to use 100 Newton for the lateral load. So we say, okay, and let me go ahead and run it. Oh, I should have, you know what, I should have done a model check and scenario check, but I didn't do it because I know that this is going to work. Let's just run it. So all this thing does is make the beam bend. Now, when you try to show the bending or displacement of the beam, you won't see anything. And the reason is that because you said this geometric nonlinear effect are on, the default scale factor becomes a 1. And this is a tiny force. It doesn't, you know, for visual purposes, you won't be able to see. If I close it, you see that? This is let me go to displacement. The biggest displacement at the top is 0.001 millimeter. Now, if you insist on seeing it, you can click on it and then select this tab. And then instead of factor 1, put the factor, I don't know, maybe 1,000 or 10,000. Let me see. See, it bent a little bit. This is only for visual purposes, but I'll put it back to 1. Okay, good. Now, what I'm going to do is, because later on I want to plot the displacement of the top point versus the uh, the uh, the reaction at the bottom, what I'm going to do is I will create some plots here because I have to do that later anyways. Okay, so let me do that right now. I'll go to plot. Here is XY plot from the field. Okay, so what do I want here? The template translation. Okay, that's good. So for the point, select the point. Okay, so I'm going to select. You know what? Before I do that, let me close that uh, and show just the undeformed shape. Undeformed shape. Good. Now let's do that. XY plot from field. Select this point, and if you're not sure what point you pick, you can always click on this and it gives you the coordinates, which is exactly what I want. The only reason uh, I deactivated the graph, the displacement, because sometimes you let the displacement be, you pick something, and it looks like it's the point that you want, but it actually will not be the same point. Okay, so here template is displacement, translation in the direction three, translation direction three. Later on, we want to do that. Direction 3, direction Z. Okay. And we say OK. So what it does, it plots displacement as a function of this dummy time. Of course, this is the dummy time. Good. So that's good. And let's do the reaction also. And the reason it looks like that bent curve is obviously nonlinear, solves a nonlinear problem. So let's go ahead and do another one. Plot from field and say, oh, this bottom point, let's do this bottom point, and we can do reaction forces, RF, and let's do it as uh, direction 3 also. Okay, almost zero. You can see that. Obviously, this is bent, so that's why pretty much they're all zero. So we don't care about this. Okay, good. Now we're gonna go and go back to scenario. We're going to go back to scenario and insert another procedure, which is another static step. Now I'm going to use these numbers, which is, uh, what is that? Uh, yeah, same thing that I did before, 0.01, 0.1. Okay, so let's go ahead and do that. Hopefully, yeah, 0.01. And this is, yeah, 0.1. And make sure that the nonlinear effect is on, and it is on. Okay, and then I apply a downward force here. So under the load, I apply a force, and that force at that top node in the direction Z is going to be minus 5.023 e to the 6. That's the buckling, Euler buckling load. Okay, good. Let me save this thing quickly, and now we're going to run it. Now, of course, it's also going to run the first step. We know that. Here are the two steps that I created. You can see that. Static step 1, static step 2, okay? And then we can do a model check, model and scenario check, which I neglected to do the first time, but that's going to be okay. This one is simulation check. Again, I don't anticipate any problems here. Hopefully, I didn't make a mess or didn't mess up that uh, force displacement curve. We'll see that. If necessary, we're going to redo it and fix it. Okay, so this is still check. It's not the run yet. Okay, good. No problem there. And then we're going to run it. Simulate and say okay. It's going to be fairly fast. If you monitor the stuff right there. Okay, let me close that. And if we go to, for example, this is step one. If you look at deflection, remember the scale is 1. Okay, so you're not going to see much if you go and look at these, or on the displacement you're not going to see much. Okay, now I can change the scale so I can see better, but let's do the static step 2. And once again, if you want, you can go here and change the scale to maybe 100 or something like that. Let's see. You can see. Actually, let's put this thing in a different view. On the view, let's look at the front view, because this is a two-dimensional problem. And you can see that it did actually deflect a little bit. I'll put another 0 here. Oh, that's because it. Let me put this thing back to 1. Actually, it deflected. You can see that it just went down here. So much force. So let's go back here. Let me go back and change the scale back to 1. Let me make it there. You can see that it bent. Okay, a little bit. Maybe if I make it 200, you can see it compresses and it goes sideways. Okay, so let me put this thing back to 1. I don't need it. Okay, so let's go back to this plot, these plots that we generated. We want the plot of displacement of the top. Okay, but I want not versus time. I want things one versus the other one. And the way to do that, let me deactivate this for a second. So you go to here, you go to plots under XY plot from expression. Okay, you click on that f of x, you say combine, and then you select displacement in the horizontal direction, and what I mean for when it's plotted horizontal direction, so x versus y, and we say okay. There we are. Now you might say, wait a minute, this doesn't look like. One more time. Okay, so let me delete all of these, delete all of these, delete all of these. Okay, here's what I did. I went to XY plot from the field. Those of you who are familiar with Abacus, that means that basically ODB file, and the template is displacement. Okay, and the translation of this node, which has coordinates 0, 0, 1000. It's exactly what I want. Magnitude of it. You say okay. There we are. Let me close that. Another one. Let me deactivate another one. XY plot from field. Once again, that point. The template is reaction force. But what I want to do is choose the concentrated force and magnitude. I'm sure if I did the reaction force magnitude, I'll come up with the same graph. There's no problem. There we are. So let me deactivate this. And now I'm going to do this XY plot from expression. Click on f of x, click on combine, select this first row and select the second one, and then say okay, and there we are. And this is exactly what I showed you a minute ago. Incidentally, okay, that's great. So my plan is the very last tutorial on this particular problem is going to be replacing the second step, static step, with the Rick step. Okay, RIKS step. All right, that's going to be tutorial 8. Good luck.